in class, I walked heel to toe around an approximate circle. I did that by simply putting one foot down with the toe straight forward, and then the next step, my other foot came down at a certain angle with the first. And I tried to keep the angle the same. Every time I'd change the angle, the toe that went down, or the foot that went down, was at the same angle with the foot that was already down, all the way around the circle. And I got approximately 13 steps. And that would be the circumference of the circle. Then I looked at where I started. I looked at the point furthest from that point, and that was going to be the diameter, and I stepped that off, and that was about 4 steps. Now, there are fractions of a step involved in both of these numbers, so I got the wavy equal sign showing those are approximate numbers, but that is what I got. Okay, so the circumference was 13 toe length or foot lengths, and the diameter was 4 foot lengths. If I take the ratio of circumference to diameter, I get 13 over 4. Now that's the approximate ratio for any circle, and any circle should have the same ratio of circumference to diameter. And 13 over 4 comes out 3.25. Okay, so we're finding the ratio of circumference to diameter. So we got the approximate ratio of circumference to diameter to be 3.25. The actual ratio is pi. That's the meaning of pi. That's the definition of pi, something nobody that comes through an educational system should fail to know. Okay, we can go outside, we can walk around a circle, we can step across the diameter of the circle. We can get out and do this, it only takes a few minutes. Or we can take a circle on paper, we can take a string and put it around the circle. We take a string and put it in the diameter, and this string will go into this string. Well, if we line it up, we can do a little more than 3 lengths of this string to make up this string. Various things we can do to really make this clear. And I actually think that that actually does get done, but for some reason it doesn't persist, and people get out of secondary school and don't know what pi means. They memorize a few formulas, often incorrectly, using the formula for area and mixing up the formulas for area and circumference, which is easy to do if you don't understand any of the meanings. Okay, another reason to emphasize meanings. In any case, now, pi has the approximate value 3.1416, which means that our 3.25 wasn't too awful bad. Okay, we're off by a little bit, about 3%. Okay, so there's the value of pi accurate to 5 significant figures. Now, we want to talk about the area of a circle. So I've drawn another circle here, and I've sliced it up into what I think is about 20 slices. I can take those slices and stack them, like so. And I don't have them all, but the last one in the stack will be up here. Okay? Now, these things are almost triangles, but this side here is really part of an arc of a circle, so there's a little bit of curvature to it. So what we get is not exactly a stack of triangles, and these sides here are not actually straight. Okay, this side of this figure that we get when we do this kind of does this. It's curved a little bit here and curved a little bit here. However, since we've got fairly thin slices, there's not much curvature. And the total length of this side is going to be half the circumference. And the other half of the circumference is over here. Why is that? Well, all these arcs here make up the circumference when you add them all. Half of them appear over here, half of them appear over here. So what we have is half the circumference here, and we have half the diameter here, because of course from this point, well, let's just take from this point to the circle is the diameter. So from here to here is equal to the diameter. So what we have is not exactly a rectangle, or a parallelogram if you prefer, but it's pretty close to one. And it's got dimensions 1/2 the diameter by 1/2 the circumference. Now if we use more than 20 slices, let's say we do 1,000,000 slices. Now we don't have time to do that. I couldn't draw it. Chalk is too wide and so forth. But you can imagine doing 1,000,000 slices. These arcs that make up the sides are going to be so close to straight lines that they really aren't going to make much of a difference in the final result. And the final result is still going to be that you have half the circumference here and half the circumference here. And you have half the diameter here. And you have something that's much, much closer to a rectangle. And if it's not as close as you want it to be, then you can cut it up into 1,000,000,000 slices. Cut it up into as many slices as you want. And the limit, as you cut it up into a number of slices that approaches infinity, this does approach a perfect rectangle with dimensions 1/2 the circumference times 1/2 the diameter. So that the area of the circle turns out to be half its diameter multiplied by half its circumference. Right there it is. Half the diameter by half the circumference. Well, the diameter, half the diameter is the radius. Okay, the circumference is pi times the diameter. Since circumference over diameter equals pi, then circumference has to be pi times the diameter. And 1/2 of that, well, we can change the order of multiplication. Half pi times the diameter could be pi times half the diameter, and that's the way I've written it here. Radius times pi times half the diameter. And half the diameter is just the radius, so now we've got radius times pi times radius. And somebody just said, well, that's pi r squared, and that's what I said earlier. And then somebody did say something about the circle with pi r squared. And what we see now is that this does give us pi r squared, and that's the area of the circle. And there's a reason for it and a construction for it. And I don't expect that that construction is something people have really seen or done much with, because nobody seems to recognize it when I do it in class. But very important construction. Again, emphasizing the idea that there's a reason behind the formula, and that in this case, as with the trapezoid, the reason is really not all that hard to understand. And as I've said before, there are plenty of formulas that are really hard to understand. You need to use calculus to derive them, and you don't have simple constructions to go by. And there are other formulas that can be done by constructions, but the constructions are far from simple and far from easy to understand. Okay, well, anyhow, here's the formula for the area of a circle with a little depth behind it, and we've talked about the formula for the area of a trapezoid or a triangle or a parallelogram or a rectangle. I can't help but think that you're going to find the formulas easier to remember if you remember the constructions. If you think about the constructions, you'll find them more believable, and I think you're going to be more likely to apply them correctly, knowing a little bit more about where they come from.